All right, let's go ahead and get started. Welcome everyone to the first meeting of the Luquillo Critical Zone Observatory for 2018. Today we'll have Emma Harrison from UC San Diego presenting on soil production response to transient erosion in the Rio Blanco watershed. Um, Go ahead and take it away, Emma.
Oh, thanks, Miguel. You can hear me okay?
Yep, we can hear you. Sounds good.
Okay,
Yes.
great. Okay, Happy New Year, guys. And thank you so much for joining this webinar and listening to me talk about this research. So the primary research questions that I'm going to be addressing in this talk are presented here. The first is, does the steady state soil production rate and/or soil depth adjust in response to topographic evolution? And the second is, are topographic metrics, like for example, the ridgetop curvature in transient landscapes, appropriate indicators for soil production? And the outline for the talk is shown here. In the first part, I'm going to talk about the drivers of topographic evolution in El Yunque and how that story was figured out, and discuss the spatial distribution of steady state versus adjusting topographic zones in the mountain range. In the second part of the talk, I'm going to introduce soil production, how we measure it and what it means in this transient watershed, the Rio Blanco, and discuss the processes that control the boundary between the soil and saprolite here. And then finally, I'll move into the topographic metrics that I think are going to be good predictors of soil production rate. So first, the topographic evolution story. So this is this is something that was figured out by Jane and Tom Miller, and it's detailed in a 2015 publication in Applied Geochemistry. The study was motivated by a kind of logical discrepancy in the data sets that existed, where the geologic studies of the bedrock had dated the rocks underlying the mountain at like 40 million years, but that didn't seem to match with the really steep slopes and high rates of chemical erosion and landsliding that had been measured by the members of the LCZO team. And how could this mountain still be persistent at its modern height after such a long period of time? So they went into a whole series of caves in the carbonate shelf that forms the western half of the island and dated sediments from inside the caves with a combination of beryllium and aluminum cosmogenic radionuclides. And the ages that they measured in those sediments indicated burial or cease in exposure to nuclide production around 4.5 million years ago in all of the caves. And so from this and an exploration of a bunch of other data that's presented in their paper, they interpreted the modern tectonic history of Puerto Rico. And sorry, a little frog in my throat. And so in the image on top, you can see the end of Miocene form of the island, which is looking really similar to like the modern Virgin Islands, a slowly subsiding carbonate reef platform. And then around 5 million years ago, activation along the Puerto Rican Trench subduction zone, which is north of the island, uplifted the platform and generated 600 meters of additional relief. And then in this image, you can see that carbonate shelf forming the western half of the island set in the foreground, and a red dashed line tracing the tilt of the shelf against elevation on the y-axis. And the tilt of that platform is projected onto the modern topography of the Luquillo Mountains set in the background. And that projection actually hits exactly a notch that exists in the topography, which is apparently like a wave cut notch formed by a paleo shoreline. So this is the story of the recent uplift event that is driving topographic evolution in El Yunque, and the subsequent questions that I'm going to ask are about how the landscape is changing and whether those changes are spatially or temporally uniform. So now I have a geologic map which is centered over El Yunque and shows the primary lithologic units that are underlying 3 of the largest watersheds. To orient, the Espiritu Santo is outlined in green, the Rio Mameas is outlined in purple, and then the Rio Blanco is outlined in blue. And the orange unit that is primarily underlying the Rio Blanco is our quartz diorite unit. And then the other primary units that we see are volcaniclastic. They're composed of interbedded sandstones, breccias, conglomerates, lavas that are all andesitic to basaltic in composition. And so lithology is the fundamental controller of landscape change, regulating weathering reaction rates and river incision rates. And so this mountain range and these watersheds that are underlain almost completely by these 2 contrasting types of rocks are a great natural experiment for probing those effects. And of course, that was the main objective of the LCZO from the outset, is to contrast these lithologies with other factors like climate and forest structure held more or less constant, or at least more constant than in other examples of mountain ranges. And so the first result that I'm going to show demonstrates the lithologic control on stream channel evolution. Because in a very fundamental way, if we want to understand the way that mountain topography will react to uplift, the first place that we should look is in the stream channels, because streams are the main source of erosive power in the mountain, and shifts in the vertical benchmarks over time are a function of the power that a stream has to transport and remove sediment. And that value is sometimes called stream power, and it can be approximated by this equation, which sets epsilon, or stream erosive power, equal to the erodibility of the parent material, which is K, the slope of the stream channel, S, and then the area of the watershed that is draining into any given point on the stream channel. And that's a proxy for the volume of water that can and will be discharged through the stream channel at that point. So a really common analytical approach to estimating stream power along a channel is to calculate this metric here, which is chi. And chi is really the integrated value of drainage area between any given point along a stream channel and the base level or the channel mouth. And so for this analysis, I first generate a flow accumulation raster, which identifies the stream channels. And then I vectorize the channels into a series of tightly spaced points. And at each point, I calculate chi. And this schematic is intended to demonstrate the power of that variable. So we've rearranged the chi equation to be the equation for a line. And you can see that the coefficients for uplift and erodibility are what determine the slope of the line plotted in chi space. So in this example, which is a steady state system where erodibility and uplift are totally constant in space, the main stem of the river and all of its tributaries plot on a single line with just one slope. But on the other hand, if the uplift rate or the erodibility varies within a catchment, parts of the stream network are going to plot with slopes in chi space, because those are the variables that set the slope. So for example, because we know that the Rio Blanco watershed is underlain by a completely uniform lithology, slope breaks in chi space are spatially explicit differences in the uplift rate. So here's the chi plot for the Rio Mameas. So it's a watershed underlain almost entirely by that volcaniclastic sedimentary rock, And the individual tributary streams are plotted with colors that correspond to their location, which you can see in the shaded relief map on the lower right-hand corner. And the tributaries in the main stem have continuous slopes in chi space, and they come really close to collapsing on each other, really like as close as possible for real topographic data. And this result indicates that uplift and weatherability are spatially constant across the Rio Mamaeus. And then there's an oblique view, which can provide some visual context for that result, where you can see that the whole channel network has this similar steep gradient. But here's the chi plot for the Rio Blanco. The lines on this plot really can be divided into a segment with a really steep slope that breaks at around 600 meters into a gentle slope. And this exists on every tributary in the basin. So since we know that the watershed is underlain by homogeneous porphyritic quartz diorite, the break-in slope indicates a significant change in the uplift rate at 600 meters elevation. And since we know that the tectonic history of the two watersheds is the same, the difference is in the time scale that it takes the more slowly weathering quartz diorite to respond to the drop in base level 4 million years ago. And here's an oblique view of the Rio Blanco with the nick zone, or the adjusting part of the stream channel, and then the terminal nick point really clearly visible in all of the gentle reaches of the upstream relict topographic zone as well. So the question we want to ask is, how does a difference like this in the stream power along a channel affect the rest of the watershed? So there's a really clear connection between stream channels and hill slopes, which I hope is visible in this shaded relief map, where the yellow line is marking the transition between relict and adjusting topography at 600 meters elevation. And that was the slope break plotted in chi space. And you can see a really dramatic difference in the sharpness of the hill slopes and the landforms above and below the erosion front. So the question that I'm going to probe in this next section is what effect, these steepening slopes, the increased erosion rate, the increasing relief, what effect does all of this have at the soil saprolite boundary? Or in other words, when we hold other soil forming factors like climate, parent material, vegetation constant across the watershed, now we have this natural experiment where we can study the impacts of topographic change on soil production. So there's really so many good reasons to study soil, and the way that you characterize soil typically has a lot to do with the discipline that you come from. And in geomorphology, there's a really specific definition for the term soil, and that is the mobilized portion of the subsurface weathering profile. So
can I ask a question in previous slide? Is it possible that I ask a question, or you want to go ahead?
I don't mind.
Okay. So I was just wondering if the steeper part is below yellow line, or is it above below yellow line? The steeper part.
The steeper part is below.
It's below. Okay. So okay, I see. All right. That was my question. Thank you.
No problem.
Thanks so much. Sorry.
No, you're fine. Thanks for asking. So how do we identify this in the field? This is the part of the subsurface that lacks the mineral fabric of the parent material, as opposed to the saprolite, which is weathered bedrock, so it has been chemically altered, but it still maintains that the fabric of the parent material, like you can see in the images there. And below the saprolite then is the bedrock, the unweathered bedrock. And so I just want to, as we look at this idealized weathering profile in the subsurface, I want to acknowledge that there are some limits to the things that we can conclude by studying the soil as I've defined it here, because there's definitely there's definitely weathering that's occurring in the soil relative to the saprolite, but we know that in our particular study area in Luquillo that lots of the weathering fronts, at least for feldspars, that's actually at the saprolite bedrock interface. And we know that the saprolite is super, super thick, and the shape of the bedrock interface is really irregular. And so equating chemical erosion as a whole and soil production it's not the right paradigm for these weathering profiles, the kinds that we're typically really well acquainted with, like in the Cacos, for example. So in theory, the unique suite of soil forming factors that converge in any given landscape result in a steady state soil production rate, which is to say that the removal of material by surface erosion is equal to the production of soil at the interface between soil and saprolite, or between soil and bedrock. And when this is the case, the thickness of the soil mantle remains constant over time. And in the Rio Cacos, which is a really well-studied subcatchment within the Rio Blanco, there is evidence from many different geochemical measures of change that the landforms are in geomorphic equilibrium. And thank you to all the people on this phone call and in the LCZO who have done decades of work on this catchment, who have made that conclusion possible. So my strategy is to directly measure the soil production rate in these two topographic zones. And the red dots are my sampling sites. And all of this sampling has been done already, and the geochemical methods are in various stages of completion. So for the soil profiles in the relict portion of the topography, I collect cosmogenic radionuclide depth profiles from the surface down to below the soil saprolite interface. And in these, I'm measuring the accumulation of the cosmogenic radionuclide beryllium-10, which is produced by spallation reactions in the mineral lattice of grains that are on and into Earth's surface at a known constant rate. And that production rate is attenuated with depth below the surface by the thickness of the soil mantle and then the bulk density of the soil. And by measuring the concentration of beryllium-10 with depth into the soil profile, you can calculate the time that it takes to produce the existing soil cover using that local production rate. The limit to this is that the cosmogenic radiation responsible for the production attenuates so much below 2 meters that the mass lost deeper in the profile has to be accounted for using an additional method. And that method is the chemical depletion fraction, which is also sometimes called the tau ratio. And that is the ratio of mobile to immobile elements in the soil, measured relative to the composition of unaltered parent material. So in the schematic representation on the right, the concentration of titanium, which is an immobile element, remains constant in the soil profile at all depths and down into the bedrock, whereas calcium, which is highly soluble, is entirely lost from the soil profile due to weathering. So I'm going to apply both of these methods in the adjusting topographic zone as well. But we know that the production rate of beryllium has changed over time because we have really clear evidence that the thickness of the soil mantles are adjusting along with the increased erosion rate. So in order to verify the production rates in this region, I'm coupling these methods with uranium series isotope disequilibrium profiles. So how this method works is that in the parent material, the decay rate of the U-series nuclides is in secular equilibrium, but weathering processes actually disrupt this equilibrium state because they affect the different nuclides in the uranium-thorium decay series differently. So leaching actually preferentially removes uranium, which is really soluble, But thorium gets retained because it's superparticle reactive. So the degree of disequilibrium between these nuclides in soil can be used to measure the time since the profile was first affected by weathering. And the technique was actually already done in the Rio Mamaeus. So we have measurements for soil production with this technique. That was a publication by Tony Dossetto and others, and he and I are collaborating to collect this data set for the quartz diorite Rio Blanco watershed. So here's a plot that shows all of the existing data globally of soil production rates that have been measured with the cosmogenic radionuclide depth profiles. And the plot space is showing point measurements of soil production rate on the y-axis and the soil depth measured at that point on the x-axis. And this is a convention that exists because there's a theoretical dependence between soil production and soil depth. And the physical mechanisms for that theory go like this. As the soil thickens, the forces that disrupt the saprolite and produce soil, like the proton flux from precipitation and the physical breakdown of saprolite by roots and frost heave or whatever's going on, all of those processes have less contact with that interface, and this slows down the production. And then as the soil profile thins, all of those processes do more work at the boundary and increase the production rate. So this global data set, which is plotted in black and white circles, are showing black circles, which are the sites with really strongly depth-dependent soil production rates, and then white circles, which are the sites where that relationship is a little less clear. And so, although my work in Luquillo isn't totally complete yet, I have some sites where all of the measurements are finished, and those are plotted in red. And one really cool thing about this is that we're really doubling the depth of soil profiles that exist in all of the empirical studies, and we're actually also the only tropical site where this has ever been measured before. So this is really improving the quality of what we get from something like this. Okay, and so the next thing here is what I've done is I've turned all of those points that we were looking at on the last plot into lines, and each line represents a different area where the soil production was measured. So I just aggregated the point measurements shown on the last slide by study area. And then I fit the points with an exponential, which is plotted in semi-log space, so it looks like a straight line. And the steeper the slope of the line is, the greater the depth dependence is of the soil production rate. So more dependent on soil depth. So as you can see, there are 3 red lines, and those are the sites where soil production rate is essentially independent of soil depth. And I just bring this up because it's been a controversy in the geomorphology community for a while, and it was the subject of my AGU talk. So people have wanted to know what makes these 3 sites fall in line with each other and out of line with the global averages. And Luquillo, by the way, is one of them. It's the one that goes to the deepest soil depths. And so it turns out that the singular commonality between these sites is that all of the samples were collected in portions of, in relict portions of transient watersheds. So it seems to be that the common link, so it seems to be that this opens up kind of a really new and interesting direction for my research in the Rio Blanco watershed, and that's the question of what controls the soil saprolite boundary in transient landscapes. And these are examples of the most extreme soil profiles that you get above versus below that erosion front line. And then here, you can sort of see the full range of soil depths across the watershed. And so on the left side, that's where we're getting those really, really thin profiles. And what this looks like is like landsliding has just taken a huge chunk out of the weathering profile and exposed pure saprolite. And now we're forming a really nice brown A horizon afterwards. And then on the right side, we have these extremely deep weathering profiles. And in these places, we're developing, you know, really thick soil profiles despite extremely low rates of erosion of particles on the surface. So they're disconnected from that depth-dependent mechanism. But then there's all of these sites in the middle. And these are kind of interesting because they're not, you know, deepening in the same way as the super thick soils, but they also don't look like they're being repeatedly exposed to landslides. Most of them are over 100 centimeters deep, and all of the soil horizons, they seem to be like relatively in proportion to each other from site to site. And so I want to address the soil saprolite boundary control in sort of three parts based off of this observation. The shallowest soils, it seems like landsliding is just taking huge swaths out of the regolith, and so that's like a definitive control on soil depth. And then in the deepest parts of the profile, it seems like what might be controlling that boundary propagating downwards is actually maybe the collapse of the saprolite under the extreme weight of the accumulated soil profile on top. And the kind of things that lead us to think that are that the saprolite and then the overlying it's a CB layer, it's like a red layer. They're mineralogically really similar, but the fabric is just gone. And so it could be an effect of the long time scale that the soil profile has been present there for, which sort of allows those effects of really slow reorganization of particles by creep to be visible. And this could be common between all of those sites that I showed with red lines, where the soil depth or the soil production rates are really too great to be explained by the soil depths. But in that center zone, that adjusting topographic zone that's not landsliding controlled, there's a model. There's a model that was first produced by Furia and Kirchner in 2010, and it shows that a steady state relationship, that at steady state, which is the gray line plotted in the background, there can be multiple relationships between the physical erosion rate and the chemical erosion rate. So at really low erosion rates, weathering increases with increasing erosion, and then in moderate erosive regimes, the weathering erosion relationship is constant. And then at the highest erosion rates, physical weathering actually decreases as a function of erosion. And all of these relationships actually make sense, and empirical data has been accumulated in support of each. So our data from the Rio Blanco is plotted as points, and it does show a watershed in steady state with relatively low rates of physical erosion. And not shown here, but reported in the original, the San Gabriel Mountains occupy that fast portion of the plot, and New Zealand is in the moderate center. And so there's a recent publication that updates this model to demonstrate that perturbations in erosion rate can create hysteresis loops of varied shapes and complexities in the relationship between physical and chemical erosion. And I'm not actually going to dwell super long on this because we can't calibrate the models, but it does demonstrate the potential of collecting a data set like this. So in the first panel, the erosion rate is increased and then it returns to base level. The weathering rate has a delayed response, but it both increases and decreases over time, as shown in the dark line, before returning to base level. You can see the relationship between those things in the hysteresis loop in the second panel, where increasing erosion rate, you know, has this effect of really increasing the weathering and then decreasing over time. Okay, the last section of the talk is really quick, and it's dedicated to the geomorphic properties of topography that are like physiologically related to the topographic changes we discussed in part 1, and that they might be really good indicators of soil production rate because of the apparent or hypothesized relationship between landscape evolution and soil production, or at the very least between landscape evolution and soil depth. And this is a worthy exercise, I would argue, because these types of metrics are super easy and fast to extract and analyze from digital elevation models. And I'd like to assure you that the other data, the geochemical data that we discussed, is not easy to accumulate. So the image here on the left is Dragonback Ridge, which is on the San Andreas Fault. And the portion of the ridgeline that's furthest away in the picture is uplifting actively, and the portion in the foreground of the picture has not been tectonically active in a long time. And you can see really clearly the rounding and smoothing of the hilltops that occurs over time. And that's represented by a schematic on the right, where we have peakier ridges. Those that have experienced recent uplift have more negative curvatures at the hilltop. And over time, erosion smooths that profiles, and the hilltop curvature becomes less negative. So as a demonstration of the concept in our study area, I'm going to return to the comparison that we made at the beginning of the talk between the Rio Mamaeus and the Rio Blanco. So the first thing that I did is generate a raster file that traces the tops of all the ridge lines in each watershed, and it calculates the curvature value for all of those pixels. And then I generated a raster of all of the first order watersheds in each basin. And I used those first order watersheds to bin the average hilltop curvatures within them. And that's plotted here with hilltop curvature on the y-axis. So increasingly negative curvatures, remember, are increasingly peaky, so sharper and sharper ridgelines, and that is moving towards the origin. So at zero, or at the origin, is our peakiest types of ridgelines, and each of the points is the median elevation of the first order basin. And the Rio Mamaeus is in purple, the Rio Blanco is in blue, and we can see that they really separate. So we have much more gently rounded ridgelines in the Rio Mamaeus relative to the Blanco, and there's a trend of increasing peakiness with a decrease in elevation in the Rio Blanco, and especially there's a few sites that have super sharp knife-like ridges in the Rio Blanco. Okay, so this is the absolute last thing, I promise. I wanted to test our watersheds behaviors against the most common kinds of model in the most common model in geomorphology that relates the topography to sediment flux. And this is a model that was developed for and in temperate climate zones, and so I thought that it would be interesting to see how similar or different our data sets are from that. And so here you can see the specific topographic metrics that I extract to do the measurements, the relief, the hill slope length, and the curvature. And I use this to calculate slopes and critical slopes, which are the steepest slopes that can exist, which are actually a little steeper than the ones that do physically exist. And you can calculate two non-dimensional variables. E star is a variable that predicting the erosive flux, and it's based on sediment transport laws. And then the non-dimensional relief, R star, is a measure of the prevalence of near critical slope gradients in the watershed. So it's how close the average slopes are to the critical slope, which is transporting like infinity amounts of sediment. So the prediction for this is shown here. It's the black line, and it is showing that at low relief, erosion should increase incrementally or linearly with increasing slope gradient until we get to a high relief place where erosion rates are starting to increase non-linearly with increases in slope gradient. And so this is basically the transition from creep-dominated landscapes where the gradient is the main control to landscapes where mass wasting processes are dominating. So now we're landsliding in the nonlinear portion of the of the curve. And so based on the evidence from the chi plots, we make the prediction that hill slopes in the Rio Blanco watershed are going to cluster near that nonlinear portion of the curve, and the Rio Mamaeus are going to cluster near the linear portion of the curve. And so I measured this for the DEMs from the two watersheds, and here's the Rio Blanco's figure, where there's the black curve that we were looking at in the previous image, and then there are data from other published studies that actually work really well with the nonlinear flux curve. So there's, although theories might argue with that, so there's the Oregon Coast Range, the Cascades, and these are all plotted in different colors. The Rio Blanco data is in red, and you can see that all of our hill slopes are falling consistently, well, are falling to the right of the predicted flux law, which is indicating that topographic metrics are suggesting higher erosive flux for any given value of R star, or the non-dimensional relief. And so I also ran this for the Rio Mamaeus, and everything else is consistent with the last figure, the other types of data. And it's hard to tell from this whether there's a true relationship, and that's because of the sparsity of the data. So plug for LiDAR coverage in the Rio Mamaeus, is we have really good spatial resolution for data in the Rio Blanco, but the Rio Mamaeus, we don't have a complete coverage data set for that. And so, this could possibly be something, but I think maybe need slightly higher spatial resolution to know for sure. So the summary for my talk, we looked at two natural experiments that exist within El Yunque. We have an equilibrium versus a transient watershed in the Rio Mamaeus and the Rio Blanco, and we can look at the way that timescale impacts the evolution of these two watersheds based off ecology. Within the Rio Blanco itself, we have a relict versus adjusting topographic settings, and within that, we find that soil depth for sure and potentially soil production rate are responding to, in a dependent way, the topographic evolution that's happening, and that the mechanisms controlling the soil saprolite boundary are varying spatially. And this is something that would be really interesting to investigate further. And finally, that the topographic metrics that we can calculate from digital elevation models are likely going to be good indicators of that variation. So thank you so much. And that's my email.
Thanks, Emma. We'll open it up for questions.
Emma, I don't have a question. I just think that was fascinating.
Thanks, Aaron. What you guys can see at the back is the LiDAR coverage. That chunk that we're missing.
Hey, so I could give us all an update on that LiDAR coverage. I'm not sure everybody's aware of this, but last March there was a mission flown by NASA. There was LiDAR and hyperspectral and a fluorescence, new fluorescence sensor for productivity, primary productivity, tree, And I think we can start to fill in a lot of those gaps. It was not an attempt to fly the whole mountain, but the flight lines produced a almost, coverage that was across almost the whole mountain. And we're trying to get that reflown with Forest Service, LTER, CCO, reflown this March, if they can come up with the money in NASA. So poco a poco on the LiDAR, I think we're going to start to develop better once we compile these images together, better relief maps of the whole mountain. And I echo Aaron's nice presentation. Very interesting.
Thanks, Bill.
Hi guys, can you hear me? So I talked to, just on that last LiDAR point, I talked to Sebastian Martinuzzi, who apparently was the person who did the NASA flight. And he writes, "I'm afraid our data will not serve to fill your gap." So that's unfortunate. I guess the USGS, yeah, I know. So I guess the USGS collected LiDAR for the entire island in 2016, but apparently they might not have covered El Yunque thinking that it was already flown. So still on the trail of LiDAR for this stupid little gap. If anyone has any contacts or leads, maybe let me know or just hand us the data.
Jane, this is Griselle.
Hi,
The person that was leading the flight was Michael Keller and Sebastian Martinucci. It's sort of a postdoc working under the project. I wonder if it would be useful to communicate directly with Michael.
Okay, I'll try that. I've heard from him before when he was writing the proposal for this second round. But my impression was that he was just going to refly, because that's what he was really interested in, is places where you could look at repeat LiDAR.
Yes, the plan is that we will refly in March to compare the before and after the hurricanes.
Yeah, but I think they might not prioritize filling in gaps if they're trying to get repeat.
I guess we will have to know exact locations, because I know Maria was very much involved with the flight too, and we always share those points where the big plots in the LCZO LTR cross proposal. And I think they flew over those, so I don't know if those sites kind of overlap to the area that you're mentioning now.
Okay, yeah. If you, I'll write to Michael and ask him what the deal is. Emma has a paper, like, just waiting for some LiDAR. The analyses are relatively simple for her now, if she can get that. So anyway, I didn't mean to hijack that. I just wanted to see if anyone had any more LiDAR leads.
That's my only recommendation right now.
One thing that was really cool that I talked to Stephen Hall about is that over at AGU was that, one of the things that people think about, sort of the maintenance of these deep soils, not just in Puerto Rico, but other places, is that there's this idea that it's, that your oxygen really is limiting at deeper depths, and that this is one of the things that gives rise to the self-arresting behavior of soil production. And what Stephen showed for that relict landscape where you have the really deep soils is that they find 15% oxygen all the way down to 5 meters deep, which is amazing. And really changed how I think about some of the soils there.
So to follow up on that, we also see it in the that pattern of high oxygen in the soil of the groundwater in the Icacos on ridges and slopes to the extent you can get groundwater from those. But then when we move into the riparian zone, of course, there is not oxygen at depth. So there's also a strong spatial zonation to the depth at which oxygen occurs. And we should think of the stream channels as through most of the Icacos basin, we should conceptualize the stream channels as really kind of armored with an anoxic zone through which the water passes as it gets from groundwater into the stream channel, with the exception of the steep flanks like the upper Guava. And so it's an interesting spatial question or conundrum as well, as having this very high oxygen deep in the soils. And then down gradient, we have this very low oxygen in soils, or at least in groundwater. I mean, the soils are shallow to groundwater. So in any case, that's a further kind of complication as we consider the whole landscape and the connection between the landscape and rivers.
Yeah.
Do we have data both like above and below the nick point on oxygen concentration with depth in similar landscape positions?
I'm pretty sure the answer is no, definitely not above and below these quartz diorite nick points.
Yeah, I guess I'm just wondering, you know, I don't know if you would expect to see a change as you went across that boundary.
I mean, you just don't get as deep of soils down below the nick points for the most part. There are some little remnant patches, but when you dig, they're much shallower. So the oxygen would have to go, you know, I think there just probably are differences because the oxygen would have to go into the saprolite rather than just in the soil. But probably it just mimics groundwater flow paths is my sort of naive guess.
Oh,
I don't know much about oxygen controls.
I think I can speak for Wendy to a certain extent, and so her data were some of the first to really measure oxygen concentration over time in soils in the humid environment like this. And in some of in the volcaniclastics, at least, there's a lot of oxygen that comes and goes. You know, there's some sites, some positions that have, and again, we're talking shallow soil air. It can change a lot over time, and then other positions, it's relatively stable at the top of the ridge and the bottom of the valley. So I had a question for you, Emma, or a comment/question that the analysis you've done first is, you know, largely focused on the Mameas and the Icacos, and which is great. We might also consider as you started out with, the Espiritu Santo and the Sonadora in particular. And the reason I say the Sonadora in particular is we know a fair amount now about that specific basin, but also that the Sonadora doesn't have the quartz diorite at the top, and the Mamaeus does have some quartz diorite, of course, at the top, and the Espiritu Santo, broadly, in which the Sonadora is a basin, also has the quartz diorite at the top. So it occurs to me that, you know, within these within these lithologic units that are largely represented by the, you know, different watersheds matching up with different lithologic units, we also have within several of them some very sharp transitions. And of course, there's a piece of the Rio Mamaeus, the Mano de Oro, that is quartz diorite down lower elevation. And so it might be interesting to, as well as this macro analysis that you've done of the, you know, the patterns and all the different geomorphic characteristics, it might also be interesting to look at these sort of smaller scale across these transitions or within these pockets of other bedrock within the, you know, a largely one or the other lithologic unit.
Yeah, I think that's a really good idea, and I didn't show it, but I did do these analyses for the Espiritu Santo as well, and the maps look really interesting. They look a lot different. They sort of have a really clear there is a really clear bedrock control in those maps. That's a slightly more complicated story than you get in either of the Mamaeus or the Blanco. But I really like the idea of doing the Sonadora too, as like a as a simpler contrast to the bigger watersheds where you have a lot of bedrock control going on.
Hi, this is Gio. I just wanted to tell Bill that one of the difficulties we had to address the changes in lithology in the Espiritu Santo and the Upper Mamaeus is that the LiDAR coverage is non-existent there. So it's really hard to study the landscape in this area due to the lack of LiDAR.
Yes, you're right. And you know, Griselle, we should maybe talk online later, maybe next week or two, about alternate ways, if there's some way we can get LiDAR flown, even whether we might be able to employ some drone technology or something to try to, I don't know. I don't know if that's technically feasible. But anyway, it's becoming a real impediment for us to advance our understanding of how these whole basins function. That's for sure.
Yes, actually there's even some talk about doing some drone work in relationship to the recovery work. So I know some areas will be flown and imagery will be taken. So I think it will be good for me to know the exact areas, you know, having GPS points.
Right. Well, we did a little, we put together, Miguel and I put together a description of the area, and I'm sure if it didn't have specific GPS points, we could generate them. You know, the issue of this hole in the LiDAR, that when we tried to get NCOM to fly it again, you know, when the initial LCZO overflight, you know, couldn't capture that area because of the clouds in May when they flew. So we could, I'll forward that on to you, or Miguel, please remind me to forward that on, and we'll make sure it comes with specific GPS points that could be used to fly it. Because I think this is a particularly good time to do it, you know.
Yes. So yes, having that document with exact points and the rationale for what they're important would be very useful for me to have handy, and I can try to, you know, how the different projects for the flight and for the drones are starting to get deployed and people start talking about sites. I can keep those in mind.
All right, great. Well, let's make sure I do that. I don't have a way to write anything down right now, so Miguel will remind me. Good, thanks.
Yep, I made it up. Sounds good. We'll get that information to you, Griselle.
will try our best, and I think there's a good chance.
Oh, yeah, this is Bruce. That was a great talk. Thank you. So I have two questions for you. My first question is that, do you know if these landscapes from your own observations or what is reported in literature, if these landscapes that you're looking at, are they slow deformation dominated, like creep dominated, or are they landslide dominated? Which one of them is a dominant form of transport in these landscapes? And my second question is that, so in some of your figures you had an indication of a best fit for S sub C or critical slope. I was wondering if you have the data, if you also have data for flux versus a slope relationship, or somebody, if you know of any literature that has the data for flux versus a slope, I mean superficial gradient, or erosion rate versus a slope or superficial gradient for anywhere near this landscape or this particular landscape. If you have that data, I can, we can try to think about. You mentioned that nonlinear flux law works very well for this landscape, and your data supports that. I think that was actually quite cool observation. But the distinction between which flux law works better is very clear if you are in the. It would be very clear if we are landsliding dominantly or we are creeping dominantly. That's my two questions. Sorry. Thank you.
Those are really great questions, and we actually have a really amazing wealth of data related to that. Thanks to Matt Larson, who has done a ton of landslide studies, and I think that landslide dominated is the answer for this area. And there is, yeah, I do think so. There's definitely soil creep processes that are happening. There's like lots of steep slopes where things are creeping down, but I think overall the mass flux is there's a lot of landsliding happening, and we can.
Yeah. So sorry, I didn't mean to interrupt. Sorry, go ahead.
No, that's okay. We can. I can share the specific data sets related to that.
So you have data set for flux, or sediment flux, or transport rate versus a slope for this landscape. That data is available.
Yeah.
Okay. All right, that's very cool. And so did you measure S sub C critical slope from that data, or you fitted the observations to what you see in your data, to what you see in the relation between relief and transport rate? Which one is the S sub C comes from flux versus slope data, or comes from a fit to the observations in the the figure that you showed?
It comes from the latter, a fit to the observations from the digital elevation.
That's cool. That's very cool. So I just want to make clear. So that doesn't so I do not disagree. It might be just nonlinear flux, and it might works very well for your observation. But the fact that S sub C is not coming from flux data suggests that the constraint on the observations does not have to be necessarily nonlinear flux law.
That's true.
If you get S sub C from nonlinear flux law from the actual data, and you put it there and you see it works, then that's I think that's more or less end of the question for me also, and I was thinking about it. But the other question you mentioned is landslide dominated. Then if it's landslide dominated, I personally do not expect nonlinear flux law work for it. Nonlinear flux law is supposed to work best for creep or a slow dominated. So that's diffusion process. That's basically the law that they have is basically a Taylor expansion of a diffusive process. And in that sense, to the degree that you can describe landslide as a diffusive process, it works for it. But as so if you go to very fast regime, I expect to see a different story. But I'm not surprised that you see if it works. I wouldn't be surprised. So it might be I might be wrong.
I'm not sure that the batteries are not. So I changed the batteries and it only went up to like 5. So maybe I should check the voltage before heading out. But we'll just have to keep a closer eye on the thing like a week.
Yeah, I think
You got the line and see if that one again. Just make sure it's like actually running the right.
Is also something that's totally tough. And I think that you know, when I say that it's a landslide dominated system, I mean like the majority of the majority of the mass that's being removed by erosion, the majority of the stuff that's getting put into the streams and transported out, it's probably, happening because of these episodic like landslide events. But the ridgelines themselves, they're not necessarily landsliding all the time. And especially in that upper relic zone, there's a lot of creep processes happening for sure. So I'm not sure that in a place like this, in a place like the Rio Blanco watershed, for example, that that just a single flux law is like a really good representation because it's so different in those two sections. I'm not sure that that's like, maybe for a steady state landscape, it would be an easier call to make.
Yeah, this is very interesting. So I would be very happy to continue discussion about this with you. I don't want to take your time right now discussing about it, but this would be really cool to continue discussion about it. I think there are things to explore.
Okay, yeah, that'd be great. Let's we'll set up a to talk more about that.
So, Behrooz, could you introduce yourself?
Hi, Jim. So I am. It's okay. Is this? So I am Behrooz. I'm a postdoc. I'm a Hess fellow at the Department of Geoscience at Princeton University, and I worked for some time with Doug Gerolmak at UPenn. That's how I know Emma, and that's how I know Jane Willenberg from the time at UPenn. And I have been working on identifying the processes that the physical processes behind the slow movement of soils, creep, aquatic creep, also known as creep, and fast landslide. So I'm trying to come up with a physical model that describes all these processes, not only slow processes, diffusive processes, but also fast, landslide type processes in a unified manner. Yeah, that's. So
Good.
So you're Bill, or is it?
Yeah, McDowell, Bill McDowell.
Bill McDowell. Okay. Nice to meet you virtually, Bill.
So Behrooz has a really cool model of soil creep that we were trying to look at, sort of this big compilation of soil production rates and see if we could come up with some sort of physical model for why soil production is the rate that it is in different places and why, and how creep might be involved in that. So we invited him to be on the call because it was a kind of a nice way of introducing the topic to him.
Right.
Yeah, Jane, and that's another question I'm very much interested in. The relation between soil production and depths, and especially vertical and horizontal soil transport across depths. That's another question I'm interested in exploring with you and with Emma. So that's. I saw the result. I just forgot about that. That was another point I got very excited about it. That you have some idea about. So that's really cool to talk about it later also.
Great.
So I'd like to follow up and go back to one point that was raised a few minutes ago, which is the dominance of landslides in erosional processes. And so I think it'd be pretty interesting. Well, I tend to agree with Emma's answer. I would see it more as a testable hypothesis that we don't really know for sure. And in the Ecocos, at least in my understanding of the main stem Ecocos, which is not all the sites that Emma's been working on, because some of those are the you know, the relatively flat headwaters of the other tributaries of the Blanco system in the diorite. But in any case, in the main stem of the Cacos, at least, you know, of course, the channel is totally filled with sand, and the banks are sand, and it's not clear what the ultimate source of the sediment that's in transport most of the time versus maybe the fraction of the total annual or decadal sort of flux comes from different sources. So if people have good ideas about how to source the sediment in the river, the provenance of where did that particle come from when we capture it, say, on a filter as it's being flushed from the basin during a big storm, I think that would be a fundamentally interesting and useful question to ask, and would have large implications for the more applied aspects of our work, which you know, people really want to know how to control where that sediment's coming from that fills up the drinking water reservoirs and exacerbates the droughts that we know are going to come again and probably will come with greater frequency in the future. So I think that's an interesting avenue to go down if people have ideas on that. So I just throw that out there.
Yeah, this is Gilles. I wanted to add that I agree with Bill that we actually don't really know what is the dominant process. There has been some quantifications. Bob Stallard has been trying to summarize the contribution of tree throw, soil creep, landsliding to landscape evolution. It's not an easy thing to do. There are a few field data, field measurements of soil creep, but they are sort of weird because they find that some deep layers are moving faster than the surface layers, which doesn't really make sense. Then, of course, when you look at the topography, below the nick points, the landslides tend to strike up to the ridge lines. But when you are above the nick points, there is a systematic breaking slope, and below that breaking slope we do have landslides that strike, but when we're above on these broad ridges we see no traces of landslides. So we seem to have an upper landscape around the ridges up there which is creep dominated, whichever is the style and type of creep, and the lower parts, the lower slopes, are more landslide dominated. Now, to which extent they contribute to the mainstream is difficult to establish. And to answer Bill, actually with Jane, we had been considering maybe using short-term isotopes to track the sources of sediment in the landscape. And it's a work that Jane had started in the Mamayes catchment a few years ago. It's something that was very preliminary in the Icacos catchment.
Yeah, so we were in this 2011 flood. We were trying to use fallout radionuclides to track the sediment. This is work with a student who then quit her PhD, and also Jamie Shanley, and this is some samples that Heather Buss eventually used for her magnesium isotope work too. And we're seeing some kind of interesting things. It looks like some of the sediment that's coming during sort of 1 month recurrence interval is coming from soils compared to sort of some of the predictions from Raphael Brass's group that most of the sediment would come from landslide derived sediment from their numerical models. So that's kind of interesting. I put another student on that paper to kind of write it up, and then she quit her PhD too. So I don't know if it's this paper or, but it'll come out this year, I promise. So So that's sort of a proof of concept that we can put in a later iteration to try to do more of that, to try to do more of that work.
Good, thank you. I actually wanted to, unless there are some more really burning questions, I thought it would be good to have time for me to give you a quick update on the project and where we stand, and I owe you a written, more thorough update because we're a fairly small group at this point. But right now the forest is almost back in business in terms of a research site. It's still not open to the public, or at least only very limited public access. You can talk your way in. Beast lay is still quite difficult, and the Forest Service is, I'm sure, working hard to try to improve access. But the weekly sampling regimes are ongoing, and a variety of work is underway in conjunction with the LTDR to quantify the impacts of the hurricane, the immediate impacts. In terms of where we go from here moving forward, we don't have a solicitation for NSF. You probably all know that. I look at who was there on the call. Most of you were at the town hall. We don't really know anything more than that. The AGU town hall on CZOs. My sense is that the next iteration, this is my bet, is that the next iteration of CZO, critical zone science, will have both CZOs in them and other ways to do critical zone science across a bunch of different sites that may or may not include the observatories themselves. The observatories may shrink in budget and stay the same in number, or expand a little bit in number, but shrink in budget to have more of the, observatory, the infrastructure of wells and long-term sampling streams, and a library of geophysical information and hydrologic balances and stuff like that as a platform and a place for a wide variety of research work to continue. We don't know that yet. That's just my guess based on what I've heard. And so in this last year of the project, I'm hoping we'll work hard to consolidate our understanding and to generate new questions that could drive the future of CZO research. And I'm thinking about what are the most exciting things that you as individuals or as working groups would see as framing a central research question for the Luquillo CZO going forward. And so after this December, so 11 months from now, we will be done with our initial 5 years. There will be no cost extensions possible. We will request and probably get some additional money to maintain the core observatory functions. And, we'll just sort of work on that as the months go by. And so you all received notice of the June meeting. I hope you received it. You were supposed to have 4th, sometime in the week of the 4th through the 8th, I guess, in June, that Monday through Friday. And then a smaller group is meeting for the hydrologic workshop that we postponed from October. And so if people are interested in attending that, some of you have already expressed interest, and the dates are Wednesday and Thursday, this is off the top of my head, the 21st and 22nd, I believe, of February. And so if you're interested in attending that and you haven't heard about it from me yet, please let me know. And we could probably support 1 or 2 more people to attend. And I'll open it for any questions in the remaining few minutes.
Bill, on the hydrologic meeting, I thought you had said the 20th, the Tuesday the 20th and Wednesday the 21st. Or is it?
No, it's
No, it's Wednesday, Thursday?
It's Tuesday, yeah, so Tuesday could be a travel day, Wednesday, Thursday, Friday is a travel day.
Okay, all right.
We want to give people the opportunity to not travel on the holiday, the President's Day. So that will be in San Juan, most likely, and Brazil has reserved a space for us at the IITF, which has electricity but only limited hours. Special delivery with generators.
So I just want to thanks everybody, and also thanks Emma and Jane for inviting me to this webinar. I have to go to lecture right now, but I would be very much looking forward to talking to Jane and Emma later about what they are observing. That was really cool. Thanks so much, guys.
Well, thank you for attending.
Thanks, Virus.
Thank you, Jane. Bye.
All right, I think we'll close it out then. Thanks everybody for attending.
Thanks so
All right,
much,
thanks,
Miguel.
folks.
Thank you.
So we will continue with this in this too small a group to make any future plans, but not right now. But Miguel will send around a request, and we'll probably stick with, from now on, we'll try to stick with Fridays as we did last semester, and so we'll set up the next 3 or 4 through the semester shortly. And thanks for attending, everyone.
Thanks, Bill.
Thanks, Bill.